Okay, this video is the first of this new topic called linear regression. This is an important topic, and we'll be talking about it for several weeks. We're going to begin with what is called simple linear regression and the best fit line. This is why I asked you to think of quantitative factors for your group project. If you take a step back and look at the bigger picture, then you'll notice that everything we've done so far had categorical factors. Every two-sample test had a binomial factor with two categories, and every one-way ANOVA test had a multinomial factor, and data was organized into groups based on what category or population it belonged to. That is no longer going to be the case. In simple linear regression, our factor is now a number, and it is called x, or the independent variable. The response variable is also quantitative, as it always has been, and is called y, or the dependent variable. The names x and y are used because it's very common to graph the variables in the xy plane. This type of graph is called a scatter plot, and here's a nice example. In this example, the x variable is years of experience, work experience, and the y variable is income. Each point in the plot represents one individual's x and y values. For example, this first point represents a person in our data set with 0 years of work experience and a salary of 20, and this point over on the right is a person with 35 years of work experience and a salary of 60. Our task is to find and analyze the relationship between x and y if it exists, and one of the simplest relationships is a linear or straight line relationship. This example is very clear. As work experience increases, then income, y, also decreases in a more or less linear way. And that is where the terms independent and dependent come from. We like to think of the y variable as depending on the x variable, or that changes in x cause changes in y. And this graph also has added the best fit line to emphasize the direction of the relationship. There is a lot of work that goes into calculating this line, and that is what this video is about. One of the important elements of the best fit line is correlation, and it deserves a few words here. Sample correlation, also called R, is a measure of the strength and direction of the linear relationship. Sample correlation is measured on a scale from -1 to +1, and here are several examples of different correlations. The first thing to notice is that a positive correlation means a positive trend, or that as x increases, then y also tends to increase. And a negative correlation means a negative trend. As x increases, then y tends to decrease. And a correlation of 0 has absolutely no trend at all. The points just look like a random cloud with no particular trend. As correlation gets farther from 0 in the positive or negative direction, then the strength of the relationship increases and the points start to look more and more like a line. The extreme cases of +1 and -1 mean that every point lies exactly in a straight line with no exceptions. That is the strongest possible linear relationship and therefore the largest possible correlation. We're going to learn how to calculate sample correlation by hand. We're going to use this simple data set to see how the various calculations work. Just remember that each line in this table is an XY coordinate pair that we can graph like this. I always find it useful to graph a data set first. Your eyes can tell you so much very quickly. For example, even though this data set is small, it clearly has a positive trend. So I would expect the sample correlation to be a somewhat large positive number. Let's begin by getting the preliminary calculations out of the way. We need the sample averages of the x and y values. These are called x bar and y bar respectively. We also need the sample standard deviations of the x and y values too. These are called S sub x and S sub y. You should verify these numbers and make sure you still remember how to calculate a sample SD. Next, there is an intermediate step called the sample covariance. And we need to get that out of the way in order to find the correlation. Sample covariance is called S sub xy, which looks a lot like the sample SD of x and y, but it's actually quite different, so don't let the notation fool you. Here is the formula for sample covariance. Our data has 5 points, so n is equal to 5, and there'll be 5 terms in the sum. Here is the beginning of the calculation. Next, we start with the first point, 1, 3. The x value is subtracted by x bar, 3, and the y value is subtracted by y bar, 5, and these results are multiplied together. And next we add the point 2, 1. And here are the 3 remaining points, ending with the last point, 5, 7. In the end, it all comes out as 4, and that is our sample covariance. All right, the hard part is already over. To go on and find the sample correlation, we just need to use this formula. It only relies on the sample covariance and the sample SDs of x and y. If we plug in the numbers, then our sample correlation is 0.8. And this confirms what we saw in the scatter plot. We expected a somewhat large positive number. At this point, I want to make a little side note about r squared, which is important enough to have its own name, the coefficient of determination. The notation gets a little loose here. Many books call this capital R squared, even though it is just the square of the sample correlation, or lowercase r. Anyway, this value is called the fit of the data. In simple linear regression, fit refers to how much the scatter plot looks like a straight line. Now at this point you may be thinking, isn't that what sample correlation already does? And you would be correct. The coefficient of determination is completely redundant in simple linear regression. However, it will become more important after we move on from simple linear regression, so I wanted to introduce it. Our example from the previous slide had a sample correlation of 0.8, so its coefficient of determination is 0.8 squared, or 0.64, which is a moderately good fit. As a side note, fit doesn't necessarily determine the existence of a trend. It is actually quite common to find data sets with bad fits, yet a significant trend. Now I want to return to the example that we were working on and find its best fit line. The equation of the best fit line takes the form that people are probably most familiar with, the slope-intercept form. The two parts of the line equation are m, the slope or gradient, and b, the y-intercept. Well, we're going to change notation for reasons that will make more sense later on. Now, b1 represents the slope and b0 represents the y-intercept. We've already have all the pieces that we need: sample correlation, sample SDs, and sample averages. The slope of the best fit line is the correlation times the SD of y over the SD of x. For our example, this works out as 1.6. It's important to find the slope first because it's used in the formula for the intercept. It is y bar minus the slope times x bar, or 0.2. So the best fit line for our example is y equals 1.6x plus 0.2. Next, I want to analyze this line to see exactly why it is considered to be the best line. The best fit line should theoretically go through the data as nicely as possible, but what exactly does that mean? Let's look at our scatter plot with the best fit line drawn through it. Most points don't lie exactly on the line and miss it by a certain distance. Specifically, we're looking at the vertical distance. The distance from a point to the line is called its residual value. The notation for residual is lowercase e, as in error. Points that lie above the line have positive residuals. Points that lie below the line have negative residuals. The third data point lies exactly on the line and therefore has a residual value of 0. And let me quickly explain the first point's residual value of 1.2. The first point has an x value of 1. And if we plug 1 into the best fit equation, then we get y equals 1.8. And that would be the point on the line directly below the first data point. Then the distance between 1.8 and 3 is the residual value of 1.2. You can verify the other residual values shown here as well. If we look at the residuals, then we see that they all add up to 0. And that makes good sense since the line should go through the middle of the data set. So some points should be above the line and some points should be below it. And these points should effectively cancel each other out, making the sum of the residuals equal to 0. But the next part is what really makes this the best line. Let's square all of the residuals so they're all positive, and then add them up. This is called the residual sum of squares. And for this example, we get a total of 14.4. It turns out that 14.4 is the minimum possible residual sum of squares for this data set. If you draw any other line through the points and calculate the residuals, then you get a residual sum of squares larger than 14.4. I don't really have the time to prove why this is the minimum. It requires partial derivatives and a lot of algebra. But our best fit line is considered to be the best because it has the minimum possible residual sum of squares. For this reason, the best fit line is also often called the least squares line. Now, because regression is such a commonly used technique, I want to emphasize how to interpret the best fit line. And I'm going to use a different example that is more realistic. Here we have pizza sales in thousands of dollars as the y variable, and the factor or x variable is student population, also in thousands. We can see in the scatter plot that there's a clear positive trend between them, and the best fit line very conveniently works out to be y equals 5x plus 60. The complete data is given over here on the left, so you can verify that if you want. The first point to make about the best fit line is that it represents the expected value of y for any given x value. So if we want to find the expected pizza sales in a town with 8,000 students, then we need to plug that x value into the line equation. Just keep in mind that student population is measured in thousands, so 8,000 students is equivalent to an x value of 8. Plug that into the line equation and we get a y value of 100, and since pizza sales are measured in thousands of dollars, this represents $100,000 worth of pizza sales. Next, I want to talk about the correct interpretation of the line's coefficient, starting with the y-intercept. The y-intercept is the point on the line where x equals 0. So the y-intercept of this example represents the expected pizza sales for a town with 0 students. The intercept is 60, so we would expect $60,000 worth of pizza sales in a town with 0 students. Note that the intercept doesn't necessarily have to be taken seriously, and in particular, it seems a little far-fetched for a realistic town to have absolutely 0 students. Next, I want to interpret the slope coefficient, and this is probably the most important number in the equation. If you already understand the slope of a straight line, this is going to be easy for you, but it's so important that I want to review it. Slope is change in y over change in x. Since the best fit line represents the expected value of y, the slope represents the expected change in y for a given change in x. Generally, the easiest thing to do is consider a change of 1 in x. Then the slope coefficient 5 is the expected change in y. And since student population and pizza sales are both measured in thousands, this means that an increase of 1,000 students would lead to an increase in $5,000 in pizza sales. Or that could be simplified to saying that each additional student adds $5 to expected pizza sales. We can also ask questions like this one. In order for expected pizza sales to increase by $1,000, the student population would also have to increase, but by how much? We just need to analyze the slope coefficient. The slope is equal to 5, which is equal to the change in y over the change in x. We want a change in y of 1, or $1,000. Therefore, we can solve this equation to find the change in x must be equal to 0.2, or 200 students. And finally, I'm going to give a bit of a history lesson about regression. An English mathematician, Sir Francis Galton, was among the first to use this technique in a statistical way, and he was the first one to call it regression. If you have a large vocabulary, then you know that regression means moving backwards, which is a pretty strange way to talk about best fit lines going through data points. But when Galton collected his famous data set, he noticed something odd that he called the regression effect. Galton's data set was an attempt to understand how a father's height would affect his son's height. So Galton had father's height as the x variable and son's height as the y variable. And very predictably, he found a positive relationship. Tall fathers tend to have tall sons, and short fathers tend to have short sons. But the weird part was that the sons weren't as far above or below average as their fathers, and that's why he called it regression. There was a tendency to return back to the center or the average height. Furthermore, there was a consistent effect that depended on the sample correlation. And when I'm talking about the effect, it is much more convenient to express height in standard deviations rather than in centimeters. The effect noticed by Galton was that fathers who were KSDs above average had sons with an average height that were only R times KSDs above average. And since R is less than or equal to 1, that meant that the sons were not as far above average as their fathers. And the same effect held true for fathers and sons who were below average height. Let's look at a simplified example to see how this works. Suppose the fathers had an average height of 174 and a standard deviation of 12, and the sons had an average of 176 with a standard deviation of 10. And let's say the correlation was 0.4. Let's begin by looking at fathers who were 192 centimeters tall. These fathers were 18 centimeters above average, or 1.5 SDs above average. Then the regression effect says that the average height of their sons will only be R times K SDs above average. 0.4 times 1.5 is 1.6. So the sons will have an average height that is 0.6 SDs above average. But now we must use the average and SD for sun's height, so 0.6 SDs above average is equal to 182 centimeters. Let's try another example. Fathers who were 162 centimeters tall were 1 SD below average for fathers. Therefore, the average height of their sons was 0.4 SDs, or 0.4 times 1 SD below average. 0.4 SD below average for sons is equal to 172 centimeters. If you don't believe the regression effect, then you can calculate the best fit line given the information at the top. And if you plug in x equals 192 into the best fit line equation, then you'll get an expected y value of 182. And if you plug in x equals 162 into the equation, then you'll get an expected y value of 172. I just wanted to give you another way of thinking about the regression line. And the regression effect is still relevant today. A good example of the regression effect is exam scores. There is a moderately strong positive correlation between midterm exam score and final exam score. Students who score well on the midterm exam also tend to score well on the final exam. But for example, let's focus on the students with the highest 5% of the scores on the midterm. It is very unlikely that all of those students will be able to repeat such an extreme success on the final exam, and their average won't be as high as on the midterm exam. Of course, some individuals will be perfect on both exams, but as a group, it is nearly impossible to maintain that level of excellence throughout, and the final exam average will almost certainly decline. The regression effect can't determine what individuals do. It only applies to the group, and it says that their average score will inevitably move back towards the mean. This example has data from 12 corporations. The X variable is the number of employees, and the Y variable is company revenue in millions of dollars. And for your convenience, I've put the sample means and standard deviations over on this side. Copy this data set down because you'll need it to answer the 3 questions coming up. Good luck with that, and check out the next video.